Hello, AV friends. Welcome to another episode of Sound Science with Sarah. Have you ever wondered what all those numbers and reporting and math might mean on data and text sheets? Well, in this video, we're going to take a look at what they all mean in the anatomy of a text sheet, specifically what all the performance values are. What is a tech or data sheet? It is a document that describes the specifications of a device. These documents can be used to understand a component in an AV system without physically having the device in hand. For loudspeakers, the text sheet can be broken down into two main parts: performance and physical attributes. In this video, we will examine the performance section of the text sheet and why each measurement matters. Moving top to bottom, we are going to start with the impedance section. The impedance stated in this section is the impedance of the transformer bypass. This means when the speaker is not being used in constant voltage mode, the impedance is 8 ohms. Without diving too deep into electrical engineering, this rating is used to calculate the resistance on an analog speaker line. Next, let's look at sensitivity. Generally, this is measured by feeding the speaker 1 watt of power and measuring the dB/SPL at 1 meter away from the speaker. Sensitivity of a loudspeaker shows us how efficient the internal components are at turning electrical energy into acoustic energy. One of the most important performance factors on a loudspeaker that can be found on a text sheet is frequency response. This is the range of frequencies the loudspeaker is capable of evenly reproducing. So, what does this range actually mean? Humans, generally speaking, can hear 20 Hz to 20 kHz. So, these ranges are displaying what frequencies the speaker can evenly reproduce in or around that range. So what are we losing if the speaker doesn't reproduce the full 20 Hz to 20 kHz? Realistically, in commercial audio, we are not losing too much. As a sample, here are some of the frequency ranges of string instruments that span the orchestral spectrum. So, if a speaker can only operate down to 52 Hz, that speaker can evenly reproduce nearly the entire range of an orchestra, with the exception of a few of the lowest double bass notes. So why are there two ratings listed? A 3 dB change is considered a noticeable change, while a 10 dB change is considered twice or half as loud. For a deeper dive into sound parameters, visit our video on frequency and decibels. Power ratings refer to the power needed when using the speaker in low impedance setting. Think of driving your car. While your car's speedometer may go up to 120 miles per hour and could handle that speed for short periods of time, if you drove your car at that speed all the time, you may end up with some mechanical issues. However, you can consistently drive your car at 60 miles per hour without taxing the system. This program power is similar to the 120 mile per hour capability of your car, while the continuous power is in line with your 60 mile per hour speed. These ratings are vital when calculating amplifier power to a speaker, as underpowering can send the speaker a square wave and damage components. Overpowering can melt voice coils. The max SPL is the upper limit of loudness a speaker can reproduce. This measurement is generally measured at the continuous power rating. This can help us understand how much sound pressure level a speaker is capable of. But again, what do these values mean in the real world? Here are some examples of sound pressure level ranges from our friend Tubi. The last major performance section is the coverage angle. This may be represented in different formats depending on if the speaker is coaxial, a standard two-way, or horn-loaded. If a speaker does not have a conical dispersion, you may see a horizontal by vertical pattern listed. For this example, we are looking at conical dispersion. Coverage is frequency dependent, so there are values given at different frequencies, and an average between certain frequency ranges. Because of their size, lower frequencies tend to be more omnidirectional. When they are added to an average, they can make the overall dispersion appear wider. Some applications require very narrow patterns, and others as wide as possible. There is no single correct pattern that applies for all sound systems. Thank you for watching and hope you enjoyed this episode of Sound Tubes, Sound Science with Sarah.